Thank you. I'll begin. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray that you be with us today. Help us to, again, Lord, just glorify you in what we do. Just pray that you help the students to study well. It's the first test approaches. Just pray that they'd use their time wisely, just to wrap up their thinking about the material up to this point in the course, Lord. In your name I pray. Amen. All right. So that brings us to Lecture 8, which is on permutations and cycle notation. All right. So I just posted lectures 8 and 9 in Blackboard. Most of 9 is done. I might add a page or so on. I need to add some pictures about something. I'm not sure if I'll get to it or not, but let's just get straight to it. So the definition here is the definition of what's known as the symmetric group on n symbols, or some people say a symmetric group on n letters. I typically call them symbols. But basically, it's the set of permutations. Use Sn. It's the set of permutations on n sub n. Now, n sub n is 1 to n. So what does that mean? What do I mean, set of permutations on n sub n? Well, remember we defined permutation in the abstract a little bit earlier in the course. What would this mean? Bijections, right? On n sub n. In other words, sigma is an element of Sn just means what? Sigma is a function from n sub n to n sub n, which is what? It's got to be 1 to 1, right? And also on to. It's got to be injective and surjective. You had a homework where you were asked to show that the group of permutations on an arbitrary non-empty set forms a group, right? So basically what you had to prove, or at least state, is that the identity map is a bijection, right? It serves as the identity with respect to function composition. The composite of bijections is again a bijection. The inverse of a bijection is a bijection, and that inverse function serves as the inverse group element with respect to function composition. And of course, function composition is associative, right? So those things together tell you that the set of permutations on an arbitrary non-empty set forms a group, right? In particular, though, when we talk about the symmetric group, we're talking about bijections on just basically the numbers 1 through n, all right? So, for example, I'll start out really simple. S2, right? There's just two things in here. Basically, you got the identity, and you got alpha. So, alpha of 1 is equal to 2, and alpha of 2 is equal to 1. So there's just two things that defines alpha. So is alpha bijection? Well, yeah. You can see it's 1 to, I mean, you can actually see it's 1 to 1. You can see it's onto, right? It's certainly a mapping from the set 1, 2 to the set 1, 2, all right? So it's indeed a function which is 1 to 1 and onto from 1, 2 to 1, 2. It's a permutation. And let's see, what else can we see? What if you look at alpha composed with alpha? Alpha of 1 is what? Alpha 2, which is 1. Alpha of 2, which is what? Alpha of 1, which is 2. So you can easily see that alpha squared is equal to the identity, right? I could make a Cayley table for this. It wouldn't cost me much time. There it is. All right. The notational scheme I'm using right now is not going to work for us going to higher n. Like, this is awful, this way of doing it. It's just awful. Completely awful. But familiar, right? I haven't said anything notationally weird yet, have I? Not really. So, our next example. Yeah, sure.
By 2, do you mean, does 2 mean alpha and 1 mean the identity? Where we have alpha 1 equals 2.
Alpha of 1 equals to 2. I mean, that's the definition.
Oh, that's part of the definition.
I mean, I'm saying that this is a function. When you plug in 1 into it, it gives you 2. And when you plug in 2 into it, it gives you 1. I'm defining.
Okay,
These define alpha. Yeah. Okay, so in S3, which is going to be what? Bijections on the set 1, 2, 3. I really, really don't want to use that kind of notation. We need a slicker notation. And a nice notation is the so-called array notation. So here, let me illustrate it for you. We could say alpha equals 2. For example, 1, 2, 3, 1, 2, 3. Actually, that's not alpha. That is the identity. What this says is 1 goes to 1, 2 goes to 2, 3 goes to 3. Kind of hard to see how this is working. Let me do an alpha, non-identity one. How about this? 1 goes to 2, 2 goes to 3, 3 goes to 1. So this notation, all right, what this means is 3 things at once. It's alpha of 1 equals to 2, alpha of 2 equals to 3, alpha of 3 equals to 1. Let me just pick out an example from a higher, let's look at S10 for a second. Then I'll come back to S3 again. So in S10, you could have, for example, sigma equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the rules for it to be a bijection is that every number between 1 and 10 can only appear once in the bottom row, because it's a one-to-one function, right? Or if you want to look at it, if I doubled up one of those, then something be left out, right? On a finite set, a function's one-to-one if and only if it's onto, right? Just like in a finite dimensional vector space, a linear mapping from the vector space to itself is one-to-one only if it's onto. Okay, so anyway, here's an example. We could go 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 5. Oops, can't do that. What could I do? 5 goes to 6, let's say. And let's see, I got 2, 3, 4, 5, 6, 1. What have I left over with here? 1, 2, 3, 4, 5, 6. I'll do 10, 9, 8, 7. There. How many different ways are there to assign 10 distinct numbers to 10 distinct spots? Lots? How many? 10 to the 10th? No. The first one I have 10 choices. The second one I have 9 choices. Then 8 choices, then 7 choices, then 6 choices, 5 choices, 4 choices, 3 choices, 2 choices, 1 choices. What's that? Yeah, I'm not talking about digits. And anyway, well, no, there's 10 choices. So anyway, long story short, the order of S10 is in fact equal to 10 factorial. Whew, that's a lot. But you notice over here that the order of S2 was what? 2 factorial, otherwise known as 2, right? There's 2 bijections on a set of 2 elements. On a set of 10 elements, 10 factorial. S3 is a little bit more manageable. What's the order of S3 if I keep working on that? 6, right? But, okay, just to make sure you guys are with me, this array notation, as it's called, you guys tell me, what would I get if I have alpha squared? Let's calculate alpha squared of 6. What would that give us? Alpha of 6, right? Which is alpha, 6 goes to what? 1. And then 2. All right. Just for example. So it's just kind of a slick way of writing case-wise notation, all right? But even this is a bad notation. Enter cycle notation. So in cycle notation, I'm gonna go back to S3 for a bit. All right. So if I have that alpha over there, that same alpha, right? 1, 2, 3, 2, 3, 1. In cycle notation, this is the following. 1 goes to 2, 2 goes to 3. That's it. Do another one for you. All right, here. I start with 1, go to 3, then 3 goes to 1. And I might write this. All right, before I do any more, let me explain to you what's going on. I have not tried to put this in the notes because my LaTeX skills are not at this level. Okay? So what you do is you just pick any number. In this case, I picked 1. And you see where it goes. So that's the 1. 1 goes to 2. So that's this 2, right? Then that brings us to here, right? What does 2 go to? 2 goes to 3. So basically I'm like 1, 2, 3, 3, and then 1 again. I don't know if that's the greatest way to do it, but and then at this point, 3 goes back to 1 again, right?
Okay. So you just kind of follow the chain of what happens and write it out in the order that it happens.
Right. You can pick any starting point. Here's 1. So 1 goes to 3, right? And then where does 3 go? For lack of a better diagram, over to here. Right? Which goes to 1. Which then, oh man, which goes back to here. A more civilized way of drawing this would be this. 1, 3, and it's just a cycle. I'm not sure whether the right picture is for 2. Maybe this. All right, let's explore this further. Are these unique? No, certainly not. There's lots of other ways we could write these. Like this, for example, I could also write as, I can basically push the number over the edge and back to the start. So this is the same as 2, 3, 1. It's also the same as 3, 1, 2. Yeah. This one, we usually just write 1, 3. That's also equal to 3, 1. All right. So the way these work, you should notice just a little bit of notation here. If I have the cycle A, B, C, all right, what this means, if alpha, let's say gamma is equal to A, B, C, what this means is 3 things. All right. It means that gamma of A is equal to B. It means that gamma of B is equal to C. And it also means that gamma of C is equal to A, right? And the same pattern I just exhibited up here can be stated for the cycle ABC. This is called the 3 cycle. Guess what this is called? A 2-cycle. Yes, we're learning. All right. Very good. So yeah, we could also write gamma equals to BCA or CAB. All right, so what do we have? For S3, I have the identity, which I'll traditionally write it as 1. You could write it whatever you want it as, though. I mean, honestly. So you get this 1. And let me try to write it in the same order as I have in the notes so that I don't go nuts. I actually, in the notes, have written out S3 in array notation, so you can look at that on page 50. I have S3 written in array notation. I'm not going to write it here, though. It could take me forever. I just want to stick with the same ordering that I chose in the notes, just for the sake of talking to you guys about it. So I got 1. I'm just going to do a couple calculations here. 1, 2, 3. 1, 3, 2. How many should we find in here? We just said a 6, right? 1, 3. 1, 2. And 2, 3. So I've got 1, 1, 2, 3, 1, 3, 2, 1, 3, 1, 2, 2, 3. Yeah?
Are we not considering the cycle that's just 2 max of 2? Or perhaps?
Well, if you think about it logically, 1. See, because all of these, I mean, if you wanted to be really obnoxious about it, oh, there's just 3. I'm an idiot. But you could also write this as 1, 2, 3. It's just writing this all the time for the identity would get really old really fast. So just as a point of writing less, I just write 1. I've seen websites that just write a pair of parentheses, but that I don't like. I just don't like it. But anyway, it's out there.
You have 2 and a 1, 3 one?
I'm sorry?
Like over here you have 1, 3, and then 2. If 1 maps to 3 maps to 1, doesn't that mean 2 maps to 2?
I'm not sure what you're talking about. I got a bunch of numbers on the board. You're telling me 1 and 2. I got 1 and 2 like 30 places here.
I'll just wait for you.
Okay, so yeah, I mean, it's good. I think your question will be answered with this calculation. So how do we calculate, for example, 1, 2, 3 times 1, 3? What was your question? There was a question. Was it one I'm about to answer, or was it something else that I wrote wrong? Oh, okay. Because I mean, if it's something like I wrote these out of order, I'd like to know that now. I want the same order here. You know, that's our convention, right, for Cayley tables. So what am I trying to figure out? I'm trying to figure out what goes in the 1, 2, 3. I'm trying to figure out what goes in this box right here. Should I do that? Yeah, I'm trying to make sure I don't do your homework for you at the moment, if you're wondering. Okay, so yes, this is one already on my table. It's safe for us. Okay, so example. Your homework is to finish filling out the table in the notes. I've got it mostly filled out for you, though. So the way this works, it's a little bit confusing in the following sense. We're still using that as a notation for the composition of two functions. And function composition still works. How? Like, if I talk about alpha beta, right? And I want to understand that, how do I understand that? This of x is equal to alpha of beta of x. Okay? That's our rule for function composition. That is not quite the same pattern as we're using for cycles, though, is it? See how the cycles are working? Cycles are working like this, right? That means that 3 maps to 1 and 1 maps to 2. So let me work it out here. So you just pick any number you like. What do you guys want to start with? 1? All right, 1. What happens to 1? What's the story of 1? 1 goes to 3. Then that gets fed to this. 3 goes to 1 again. Oh, well, the circle's complete. There's just a 1. All right. What's next? You can either pick a 3 or a 2, whatever you want, just something else. I'll just pick a 2. So 2, you feed 2 into the right cycle. What happens? 2 goes to, this 2 doesn't go anywhere under this one, right? 2 goes to 2. Then it goes over here, 3. And then to clean it up, we just write 2, 3. So what goes in the box? Oh, uncool. 2, 3. Yep.
So like if a number doesn't appear in this cycle notation, we just assume that it knows itself.
That's the convention. That's what the notation means. Let's see here. Let's work out this second row here. You guys already know what goes. Ow! Yowzers! Better. I'm tired of almost scraping my hands to pieces on stuff because there's not quite enough room in here between the umbilicus and. You guys know this. I don't really need to write this. I'm just writing it because it doesn't cost me any thinking. The identity, right, times anything is the thing again. But the second row requires a little bit more calculation. What's 1, 2, 3 times 1, 2, 3? One, 2, 3 times 1, 2, 3. So you start with anything you like. 1. All right. You guys are so boring. Sorry. 1 goes to 2. Then I go over to here. And 2 goes to 3. So I write 3. I don't write the in-between step over here. I only write what you get when you get all the way to the end of it. All right? So then I go, okay, 3. So I go back to here. 3. Where's 3 go to? 3 goes to 1. Then where's 1 go to? 2. We're done. Once you have all 3 numbers there, you're done. So 1, 3, 2. I should really do this in some other color. What should we calculate next? How about let's calculate 1, 2, 3 times 1, 3, 2. Again, 1, 2, 3 times 1, 3, 2. All right, so we start at 1 because you guys are going to tell me that. 1 goes to 3, which goes back to 1 again. Oh, that's just, now we're not done yet. Now there's still other numbers to check. How about 2? What happens with 2? 2 goes to 1. 1 goes to 2. Oh, I'm starting to believe. Let's check. Just double check our calculation. 3 goes to 2. 2 goes to 3. So yeah, you guys are right. It was the identity. But I don't think you could have known that when you said it. So that's why I didn't agree with you.
So we could have gotten that equals 2, 3.
Yeah, you could have gotten 2, 3. Although, in your defense, the Latin square says it's not 2, 3. But it is good to be redundant in your calculation as well, right? So there's a danger in using something as true when it's false. All right, it can lead to other falsehoods. 1, 2, 3 times 1, 2. What do we get? All right, so we'll start with 1 because you guys want me to. 1 goes to 2. Then 2 goes to 3. Okay, so 1 goes to 3. Then what happens with 2? Excuse me, what happens with 3? So 3 goes nowhere. And then here 3 goes where? To 1. Ah, the circle is complete. All right, and then 2 goes to 1, but then 1 goes to 2, so 2 is a closed cycle. So it's just 1, 3. Now, if we trust ourselves, we can already tell what goes here, right? So I'm gonna believe in ourselves. What goes there? 1, 2. All right. Let's see here. Excuse me. So we've calculated here. Let's calculate this one. What do we get if we calculate 132 times 123? What's that give us? 1 goes to 2. 2 goes to 1. 2 goes to 3. 3 goes to 2. 3 goes to 1. 1 goes to 3. So you are correct. We get the identity there. Curses. That's not what I wanted to do. Let's try 1, 3 times 1, 2, 3. Yeah, 1, 3. One 3 times 1, 2, 3 is what? 1 goes to 2. 2 goes nowhere. And then 2 goes to 3. 3 goes to 1. Closed cycle, right? And then 3 goes to 1. 1 goes to 3. So 3 is just 1, 2. So the reason I did that mostly is because I want to focus your attention on something not that surprising really, but check it out. We now have a what? Another example of a what kind of group? See that? That says that, exactly what we said, non-abelian. That says that 1, 3 times 1, 2, 3 is not equal to 1, 2, 3 times 1, 3. Right? This is what? This is 1, 2, whereas this is 2, 3, right? And these are not equal. So S3 is non-abelian. In fact, you can prove, I think this might be one of your homeworks, to prove that Sn is non-abelian for n greater than 2. I proved the 3 case for you. Are you happy? Okay. All right. So now that we've gotten our feet wet in this cycle notation, let me state a theorem for us. Oh, man. I wanted to leave that. What was my first 3 things? What did I have here? 2, 3, 4? All right, so let's write this thing in cycle notation. Right? We should do that while we're at it, since I already have it here. I start with 1, since you guys want me to. 1 goes to 2. 2 goes to 3. I'm sorry, 1 goes to 2. 2 goes to 3. 3 goes to 4. 4 goes to 5. 5 goes to 6. 6 goes to 1. Oh, closed cycle. So basically, like, you can think about it. So it's like this. I don't recommend using these diagrams. They're not that useful, right? I'm sorry, I've forgot my, all right. Then where we get to 7. 7 goes to 10. And then it goes back, right? So 7 to 10. My diagrams are not that great on the arrays. And then 8 and 9 also form another little cycle. How many cycles are possible for a permutation? N? Yeah, I guess N is, if I allow for 1 cycles. But yeah, I mean, as many symbols as you have, certainly, but usually less, right? I mean, if you're looking at 2 cycles and 3 cycles and so forth. But can you have more? Well, actually, I have to disagree with you a little bit, Mr. Bradley. I'm sorry, Mr. Call a spade a spade. Call a Hoogerworth a Hoogerworth. See here. How about this? 1, 2, 3, right? Is also equal to 1, 2, 3. Check this out. 1, 2, 1, 2, 2, 3, 2, 3. You know, 1, 2, 1, 2. Dot, 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 dot. 1, 2, 1, 2. So you can always insert copies of the identity, right? So it can go on and 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 on, if you want to, because we're allowed repeats, right? So like, actually do a calculation here. If I have 1, 2, 3, 4, and then I've got 3, 4, 7, like that, I can simplify this, right? Now these are an example of cycles which are not disjoint. See, when we multiply the cycles, we can multiply them and create a pair of disjoint cycles, or or in that case, 3 disjoint cycles, right? If you think about it, you're just going to like go through the numbers, right? So you start with a number, and it gets connected to another number. It gets connected to another number. At some point, you either exhausted all n of your numbers, so you've got an n cycle, like 1, 2, 3 in S3, or you loop back, right? At which point, you pick a number you haven't already hit, and then you start going from there, until eventually you either exhaust the numbers or you loop back, right? So I can rewrite this as a pair of disjoint cycles, or perhaps 3, I don't know how many. Let's try it out. 1, 2, 3, 4, that's easy, because, oh, I'm an idiot. I have to go this way. Sorry, guys. Oopsie. 1 goes to what? 1 goes to 2. And then how about 2? Well, okay, 2 goes to 3, fine. We're actually fine already, but I'm not thinking about it, right? 3. Uh-oh. Well, 3 goes to 4. I guess we're still okay. Oh, no, 4 goes to 1. Right, so that's that. Thank you. Let me see here again. 4, so everybody agrees on 1, 2, 3, and 4. But what happens with 4? 4 goes to 7, right? Oh, 7, you're right.
No, it's 1, 2, 3 parentheses. No.
You're right. All right, let's try this again. Start with 1. Where's it go? 1 goes to 2. I'm sorry, you have to go this way, okay? So 1 goes nowhere. And then over here it goes to 2. So we get to 2. Then we go in here. What happens with 2? 2 goes nowhere. 2 goes to 3. I go back over here. And where does 3 go? 4. What happens with 4 here? Goes to 1. Very good. Some of you already had this. Excellent. Now we're to 4. Because, well, or you could start with 7, whatever you want. You could start with 6. What happens with 6? Goes nowhere. I mean, that's true, right? So 6 is like, okay, it's not doing anything. How about 5? I mean, this and this are just non-events, but 7 goes to what? 7 goes to 3. 3 goes to 4. Of course, we omit those, and what do we have? We've got 1, 2, 3, and then you can either write 7, 4, or 4, 7, whatever you like. I'll write it 7, 4. Disjoint cycles. Let me make an obvious theorem for you. If alpha and beta are disjoint cycles, then what can we say? Alpha beta is equal to beta alpha. In other words, disjoint cycles commute. How would you prove this? So I have a proof in the notes, by the way, that any permutation can be written as a product of disjoint cycles. I think my time is probably better spent in here if I show you lots more numerical examples as opposed to going through that proof. The proof is what I just said to you, though. You start with a number, you follow it as far as it goes. It either loops back or exhausts the set, and then you just go on to the next number and keep doing this every time picking a number you haven't already hit. what you're left with after that process is disjoint cycles. That's really the proof. This one's a little bit more instructive, so let me do this one. If we have alpha equals to, let's say, a1, a2, ak, and we have beta equal to b1, b2, bj, where what? You know, basically I want a1, ak intersect b1, bj to be what? Empty. Let's see here. So if that's the empty set, in other words, they're disjoint. And of course, I'm assuming that these are two permutations in Sn, right, for n sufficiently large. So we need a little bit of terminology. We say that x is fixed by sigma if sigma of x is equal to x. And we say x is moved by sigma if sigma of x is not equal to x. So a permutation either moves or fixes every number between 1 and n, right? So I need to come up, I'm tired of writing these sets up here. Let me give this a name. Let me call this thing A. Let me call this thing, I guess I can use script db. So if you look at n sub n with removing the union of A and B, right? What are you left with? So if, let's say, if you have x an element of here, all right, then what? Then alpha of x is equal to x, and beta of x is equal to x, right? That's something that doesn't appear in either cycle's list, right? So those kind of numbers are not moved by either of these permutations. In principle, there may not even exist such an x, but that's fine. We have to address the possible case. Okay, so like, so in this previous example here, if you want to think about that for a second, we've got that this, I'm claiming that this is equal to that, right? As an application of this theorem, right? So the part I'm talking about right now, what would x be as it relates to this example? What kind of, yeah, 5 and 6 would be like the x I'm talking about at this point in the theorem. In any event, clearly, alpha of beta of x is equal to beta, is equal to what? Alpha of x, which is equal to x, and also beta of alpha of x is equal to beta of x, which is equal to x. So clearly alpha beta is equal to beta alpha on these sorts of numbers. Okay. Continuing, we have what? We have alpha of b sub I is equal to b sub I for each b sub I in B. Right? Because they're disjoint. So by the definition of cycle notation, the cycle alpha is not moving the b's. Right? They're stationary. Conversely, what else do we have? Beta of what? Of let's say AI is equal to AI for each a sub I in A. What else do we know? There are two more facts we know that we should list. Let me number these facts for our convenience. 1, 2, 3, and 4. What are 3 and 4 here? Yes, sir. That is not the, well, that is true, but not quite what I want. I mean, you're right. Fine, I'll take it. Alpha of a sub I is equal to a sub I plus 1 is true right up until it's not, which is k, right? So let me just say instead of this, which cuts more to the point, is an element of A. That's the spirit of what you're saying. And B, it just avoids me, it helps me avoid breaking into cases. This is an element of B, right? Beta of B sub I is an element of B. So now we have everything out in front of us. We have the notation set. We can compare alpha of beta versus beta of alpha on the sets A and B. All right? So first thing, let's look at the points in A. What happens? So if we have alpha of beta of a sub I, that's equal to what? Alpha of a sub I. Why? Because beta of a sub I is a sub I. Beta fixes A, all the A's. Right? On the other hand, beta of alpha of AI is equal to what? No? Well, alpha of AI is an element of what? A. So what does beta do to any element of A? Right, I mean, maybe if instead of writing an a sub I here, it helps if I just say like that. I don't know. This is a variable statement, okay? Don't make too much significance to the a sub I. That's not a fixed thing, that's a variable. So my point is that this is an element of A, and beta fixes elements of A. So this is, again, alpha of AI. So what do we get? We get that this and that are equal, right? So alpha beta of AI is equal to beta alpha of AI, right? For all AI in A. Likewise, what else? Likewise, you can calculate that alpha beta of BI, right, is alpha of beta of BI, but beta of BI is an element of B. Alpha fixes elements of B, so this is exactly beta of BI. And beta alpha of BI is beta of alpha of BI, which is beta. See, alpha of BI is just BI again. So check it out, they're equal. So therefore, alpha beta of BI is equal to beta alpha of BI for all BI in B. Thus, alpha beta of Y is equal to beta alpha of Y for all Y in N sub N. Hence, alpha beta is equal to beta alpha. So there you go. There's the proof that disjoint cycles commute. See where I am here. Uno momento. I actually have the proof that the proof that every permutation in SN can be expressed as the product of disjoint cycles. That's actually at the start of lecture 9. I forgot. I was writing this and then I split it into 2 pieces. Forgot where I split it. So we have now made it all the way to lecture 9. Are you excited? A little bit excited. All right. So what I'm going to do, rather than diving into lecture 9 formally, I'm just going to do some calculations from lecture 9 for you. All right. So Yeah. You know, actually what I'm going to do, I'm going to look at an application. So we talked about D3 before, right? Remember the dihedral group, order 6? How you guys want me to number these? 1, 2, 3, whatever. It has been complained to me by the grader that my numbering on the pentagon is opposite the direction of my rotation, which messed with his dyslexia, as he said. I'm sorry about that. I regretted it once I wrote it, but I didn't have anything to white out my pen. So I was like, I had to commit to it. I'm not saying it's best. That's really a nightmare for him to grade. Anyway, I digress. So, you know, there's different things we do, like rotation, which is what? So we got what? 2, 3, 1, is it? So you could think of the rotation as being what? It's like what? One goes to 2. 2 goes to what? 3. Right? You could think about, let's see here, what else did we do? Something like this guy, right? So what was that? That was the flip. So how'd the flip work? 2 stays put, and 1 and 3 flip, right? So it looks like the flip should be kind of like what? 1, 3? All right, let's try this out. So F R F is equal to what? Our inverse, allegedly, right? I mean, not allegedly, we proved that. But let's see here, let's try that out. What's that look like here? 1, 3, 1, 2, 3, 1, 3. What happens with that? Let's just see how far this analogy goes, right? What should we expect? What's our inverse? See, it's the clockwise rotation, right? So it's 1, 2, 3, right? Which is what? Kind of like 1 goes to 3, 2 goes to, 3 goes to what? 2, and 2 goes to 1, yeah. So if there's any justice, I sure hope that works out to this, right? If this analogy is going to be complete, is it? So let's try it. 1, 3. Start out with 1, right? 1 goes to 3. 3 goes to 1. 1 goes to 3. What happens with 3? So I get to 3. 3 goes to 1. 1 goes to 2. And 2 stays put, so 2. Then I get to, I mean, I know what's going to happen now. If I track through 2, though, what happens with 2? 2 goes nowhere. 2 goes to 3. 3 goes to 1. So 2 goes to 1. Circle's complete. So this goes to show you we could also look at the dihedral groups in terms of permutations of the vertices in this way. And you could calculate stuff in the dihedral group using permutations. But I don't want to. Not yet, anyway. Anyway, so next time we will look much harder at 2 cycles. We're going to find that any permutation can be written as a product of 2 cycles, either even number or odd number. I have another homework for you guys. If you didn't get your homework already, they're up there if you came in late.